Hi, in this video we're gonna look at tables, and also you're gonna see more like word problems, and we're gonna particularly look at a closed system, which there's no mass transfer, but there's a there's an energy transfer, and we're gonna look at rigid tank. Rigid tank means the volume stays constant. Okay. So first problem. There's a 1.8 meter cube rigid tank contains steam, so that means it's water. At temperature is 220 degrees Celsius. So while you are reading it, write down what's given. And 1/3 of volume is liquid phase. And what does that tell us? Which means the rest is vapor. That tells us it's gonna be saturated. We know this is going to be saturated liquid vapor mix. If we know that, we also know quality, because one part is liquid, two part is vapor. So that's going to be 2/3. That's going to be the quality, right? 2/3. Because quality is mass of the vapor over total mass, so it's 2/3. And then knowing that, we needed to find what's the pressure, and also need to find the density rho of the mixture. Okay, and they also find the quality. We already kind of know the quality. Quality is 2/3 for this problem. So this is actually quite straightforward, because we already know the phase and then know the temperature and the quality. So in order to solve it, you know the temperature, we're just going to go to temperature table, which is table A4 for water. Then find out 220 degrees Celsius. What's going to be pressure? Pressure going to be, since it's saturated, it's going to be the saturated pressure at 220 degrees Celsius. So that's our task. So let's go for 220 at saturated temperature. Do we have 220 here? Oh yeah, we're lucky. So there is 220. If not, you're gonna have to use the linear interpolation, right? And we're reading the saturated temperature, which is 2319.6. 2319.6 kilopascals. So you solve that. That's gonna be our pressure. Then quality is 2/3. If you're gonna use that in percentage, I believe it's that, right? And then the last one, the density. Well, in thermodynamics, we don't use density that much. However, we know density is basically reciprocal of specific volume. And so can we find a specific volume for this problem? Specific volume, again, this is a mixture. Then we're going to use that equation for mixture, VF plus X VFG. And do we know VF? So we're going to go to the same table, A4, since we know the 220, find VF. 220, do we know the VF? It's this value, 0.00119. And the quality is 2/3. And we're going to times VFG, which is VG minus VF. And it's going to be 0.086094. Did I do it right? Yes. Okay, I think we're good. The minus 0.00119, that's our VF. Then you can find our specific volume. Let's put in the calculator, see what we got. I'm gonna pause, see what you have. So then I got 0.0578. That's our density. Oh, I'm sorry, that's our specific volume. And take a moment to think about if this number is reasonable, right? So the quality is about 2/3. So it's a little bit more than half. and the VF is very small value, 0.00119, and VG is 0.086. So it will be closer to VG since this number is greater than 50%. And so I think this number is reasonable. Now, let's have a unit specific volume meter cube per kilogram. To find our density, it's going to be 1 over V. So what do we have for that? So reciprocal of that value. That gives us 17.3 flip mass per volume for density, kilogram per meter cube. So that's the density of this mixture. Okay. So now I'm taking a moment to relook at this problem, and I realized I never used this mass. I never use this volume because there's a volume given, 1.8 meter cube. I never used it, right? Well, that's all right. And that's a noise maker because I don't need to use that to find out anything. I don't need to use that to find the pressure. I don't need that to even find our specific volume. And then therefore I don't need to use to find the density. However, if they ask you what's the mass, what's the total mass, then you need to use this, right? All right, so that's all I have for this problem. Now let's look at the next. For this problem 3.42 is that there's 10 kilogram R134. The reason I choose this problem is we are going to introduce R134 table. So far we have been always dealing with water, so steam table, but R134 has a set of tables as well. Okay, so be mindful when you're solving the problem. If it's water, going to steam table, which is A4567. If it's R134, we're going to go to the right table. Let's see where they are. Okay. So first of all, I'm going to go to table of contents. 4567, that's going to be our steam table, but the pressure, the R134 is going to be 11, 12, and 13. Okay, 11, 12, and 13. So I'm going to make a note. If it's R134, the table is A11, 12, and 13. If it's water, we're going to look at table A4, 5, 6, 7. All right, okay. So let's write down what's given while we read this problem out. So its mass is 10 kilogram, and it's R134. Pressure is 300 kilopascal. And it's in a rigid container, so in other words, our V is a constant, V1 equal to V2. If they have an initial volume and final volume, it's going to be the same, constant. And it tells us the volume, big V, is 14 liter. Determine the temperature and the total enthalpy. So they want us to find the temperature, T, and also total enthalpy. So it's going to be big H, not specific enthalpy. Then they also said the container now is heated until the pressure is 600 kilopascal. So now you see this problem have a different layer. It has a process, has a path, right? This process allows to get us from state 1 to state 2. In that situation, I often go back to write down this is going to be P1. That's our state 1. Okay. Now the pressure is P2. So I'm going to write down below here. Our P2, state 2, is 600 kilopascal now. Now, earlier they want to find the temperature and total enthalpy in the container. That's for state 1, so T1, H1. After the pressure is up to 600 kilopascal, they want us to find the temperature. That's going to be final state, T2, and enthalpy, H2. Right, so that's what we needed to write down in terms of find and in terms of given. And that's important for thermodynamics, to read it and write it down, given and find. All right, now how do we solve this problem? Each state we're going to solve individually. For state 1, we need the 2 properties in order to find the other one. What's the first property? The pressure is 300 kilopascal. And what's the second property? They give us the volume, and this volume stays constant. So we want to find a specific volume, V1, small letter. It's going to be big volume over mass. Then we know the volume is 14 liter. And the mass is 10 kilogram. We're going to change the letter to meter cube. We know 1 meter cube is 1,000 liter, right? In that situation, liter cancel out. We will get our unit as meter cube per kilogram. So it's 14 times 10 to the negative 4. And to make that better looking, it's gonna be 1.4 times, why don't we just use decimal? So it's gonna be 0.0014, right? Meter cube per cubic, not kilogram. All right, so we know the 2 property now for the state 1, pressure and specific volume. Then they want us to put at state 1 what's the temperature and enthalpy. Now we can do, it's just like how we look up the table for the previous ones, and now it's just kind of embedded to a problem, to like a word problem. So how do we do that? So we know the pressure. We're going to look at our pressure table. First of all, we do not know what phase that is, right? We do not know, so we need to use the second property, which is our V. We're going to find our VF and VG at 300 kilopascal to compare our given V to VF and VG. So shall we look for 300 kilopascal? Let's go to, oh, whoa, hold on a second. I just made a cardinal mistake. Why? This is not water. This is R134. So do I use A5? No, I don't. And hopefully you learn from me. Catch up the mistake and just fix it. All right, so we are not gonna use A5 anymore. We're gonna use what we said, 11, 12, 13. So let's go look. So 11 is temperature table, 12 is pressure table. So we know we're going to go to table A12, the pressure table. So A12 at 300 kilopascal. So that's our A12 pressure table at 300 pascal. Well, what do we notice? There's no 300 kilopascal. The one that's wrapped around 300 kilopascal is 280 and 320. Well, we're gonna use linear interpolation, but this is a special linear interpolation. Why? 300 is the average. It's a midpoint between 280 and 320. So you can just use average to figure it out instead of using linear interpolation. Well, you're gonna get the same answer anyway. What do we care? We want to find the V and we want to find the VF and the VG, correct? Okay, so let's go look. VF, since this is a midpoint, 300 is midpoint between 280 and 320, so we're gonna use those two values right here. it's a small value, right? So I'm gonna actually take a picture of that and then put it over here, or how about this? It's gonna be VF is 0.0007699, and at 320, hopefully y'all look at the table, it's 0.0007772. All right, then VG is gonna be the same thing. All right, so go back to VG here, and we'll have VG 0.0. Okay, well, 0.07232, and the next one is 0.063063604. All right, so those are the two numbers we're getting for our VG. Just double check. It's going to be those two numbers, okay, for 280 and 320 degree. Then divided by 2. Let's see what we got. And our value here is 0.068 rounded up meter cube per kilogram. Okay, so far we just go to the pressure table to use a linear interpolation. Here is the average to find out VF and VG. And since our second property is V, we're going to compare this value to VF and VG. And I just realized I didn't calculate the VF yet. So I'm going to go ahead and get that numbers. So the value we got for VF is 0.000077355. Well, it's so many decimals. Okay, so that's meter cube per kilogram. And let's look at this given V. This given V is obviously in between those two values, between our V. Here is between VF and VG. Then, oh, that's all we need to know, right? Then we just need to know, all right, then this is going to be our saturated liquid vapor mixture. So in that situation, we'll have saturated R134 liquid. We also have saturated R134 vapor. All right, in order to find our temperature, then we're gonna go, we know it's a liquid vapor mixture. We can go back to the same saturated table, the pressure table, A12. We're gonna figure out, okay, the T here, the pressure, the T here is gonna be our saturated temperature at 300 kilopascal, and likely we're gonna take the average again because there's no 300 table. So let's go over here and we look at 280 and 320, and those are the two temperatures, negative 1.25 and 2.46. We're going to take the average of those two. So go back over here. It's going to be negative 1.25, that's for 280, and 2.46, that's going to be our 320. And when we do average between them, we're going to get an answer as 0.605. That's going to be the temperature at that. So that's initial state, T1. Then we also need to find our H1, right? So for H1, it's a mixture. We're going to use our formula, which is HF plus XHFG. And do we know X? We do not. We only know it's a mixture. However, we know this specific volume. And so we're going to put this on hold. We're going to find our X first. How do we find our X first? Remember, our V, we know V, so we're going to use V as the jumping board. So V is equal to VF plus X VFG. This is for mixture only, right? And this is indeed a mixture. So in the future, you're going to just write down x, just going to be equal to V minus Vf divided by Vfg. So in that situation, your volume is 0.0015. All right, this problem, it is a little tedious. Now I'm finding out. And Vf is going to be 0.000777355. And our Vfg is going to be Vg minus Vf. All right, so then we can find our quality. So pause for a second, see what you got. So here the answer I got is quite a small number. It's basically 0.93%. In other words, it's 0.0093, right? That's what I have. So this number is really small. What does that mean is, this means it's very small amount, it's vapor, majority of the liquid. And now let's look at this number. This is the given volume. It's pretty close to this Vf, and it's quite less than this Vg. Well, so that might make sense. All right, so that's our quality. And now we can go back to this equation right here to find our H1. H1 is HF plus XHFG. And our HF, again, we don't have that 300 kilopascal, so we're going to go back to the table to find the average between 280 and 320. HF is going to be those two values, 50.18 and 55.16. So I'm actually gonna take a picture on this one. So it is half of 50.18 plus 55.16. That's our HF. And our quality is going to be 0.0093. You calculate it from specific volume. HFG is going to be difference between the two. Again, we're going to use linear interpolation using the HFG in the table A12 to get those values. Okay, so we have this value, then we can find our HF. Pause for seconds, what you got? So putting the calculator, we calculate the H1, the specific enthalpy as 54.51 and kilojoule per kilogram. And remember, for this problem, they're asking you about the total enthalpy, right? The total enthalpy, so it's big H, and they do give us the mass. Then we can go ahead and find out big H. So big H is going to be the M times H1. Mass 10 kilogram times H, small h, 54.51 kilojoule per kilogram. Then that cancelled out. That gives us 545.1 kilojoule. Wow, this is a non-problem, I have to admit. That's going to be our total enthalpy just for state 1. However, we're going to look at state 2. Alright, that's just state 1. Now get to state 2. State 2, we also are going to do it individually, and we just need 2 separate property. Do we know 2 separate property? Let's see, we know the P2. So do we know the second property? Well, if you thought about specific volume, then you are on, because this is a rigid tank problem. If it's a rigid tank, V1 equal to V2. We have to use that relationship in order to get our second property. So now I'm going to write it down, our state 2. Our P2 is 600 kilopascal, and our specific volume V2 is equal to V1, which is equal to 0.0014 meter cube per kilogram. So those are the 2 properties, okay? And I believe we are trying to find a T and H also. So how do we do that? if we go, hopefully this time we don't need to find a linear interpolation. We have the table right there. So which table? A12, because it's R134. So go to R134 table, and it's a 600. Yes, we have 600. And our V, before we do anything, we need to compare VF and VG. Our VG, our V is 0.0014, so it's between those two values of VF and VG. So we know it's also a liquid vapor mixture for state 1. Okay, for state 2. State 1 and 2 doesn't have to be in the same phase. It can be different. For this problem, it's the same. So we're going to write it down at this one at 600 kilopascal. From table A12, hopefully you get the same VF I'm having. It is 0.0008199, and our VG is 0.034295. So knowing those two, and our V is between, our V2, state 2 is between VF and VG. So we know it is, again, saturated liquid vapor mixture. We kind of go in same system here now. If it's a mixture, in order to find our temperature, T is going to be Tsat at 600 kilopascal. So going back to table A12, let's see what is going to be the Tsat. It's going to be this value, isn't it? 21.55 degrees Celsius. Then in order to find our enthalpy, we need to find a quality because it's a mixture. So the quality we needed to find out from specific volume. So using the formula V minus VF divided by VG minus VF, right? So it's the same formula we used earlier. V here is going to be same as V1 because it's a rigid tank. However, our VF is different because it's at different pressure. It's 0.0008199, and here VG is going to be this value, and our VF is this value. Okay, so hopefully we'll find our quality. Pause, see what you got. So the number I got is 1.73%. So it's 0.0173. Okay, and again that shows this is pretty much all liquid, right? Because only 1.73% is vapor. The rest, 98%, it's our liquid, because this number here 0.014 is close to VF. So knowing that quality, we can go ahead use to solve specific enthalpy. Using this formula, we can go ahead and find our HF. So going back to the table, we can go ahead and find out what's HF value is 81.51. And then our quality, you calculate as 0.0173. And you go to the table, you can find our HFG, which is 160.81. That's from this one here, right? Oh, yeah, I actually got wrong. It's 180.90. Glad we check here. So knowing that, we can solve our H. Pause for a second, see what we have. So the answer we have here is 84.64, and that's in kilojoule per kilogram. That's our H2. Then find the total enthalpy. We're just gonna use mass times H2. Mass is 10, so we got 846.4 kilojoule. That completes this problem, right? Okay, I didn't know this is a longer problem than I think, but this is great because this really involves a lot in this problem. It has rigid tank, so you have to use V1 equal to V2. It's R134, so the right table. The second one, in order to find the enthalpy, you're going to have to find quality. So in order to find quality, you are using the specific volume to find quality first. So those are just great information there. That's something you're going to actually use it for your problem solving. So it's worth the time. All right, see you next time. Bye.